Hello students, welcome to chemistry class. Today we're going to be discussing about the topic titled acids, bases and salts. Acids, bases and salts. So as you all know, my name is Zoelami today, and don't forget the normal procedure. Before starting this class, make sure you are not distracted and make sure you are with your notebook and pen, as the case may be. So over to our objectives. At the end of this class, before I go ahead, I would like to tell you that when we have a voluminous topic, we do divide the objectives into two. That means the part 1 will be treated in this class, and by the next class we'll complete the topic by discussing the part 2. So on part 1, which is today's class, we're going to be looking at the end of this class, we must be able to explain theories of acids and base. There are some theories that people propounded and later it was accepted. So we have to know all these theories of acids and base. At the same time, the second point is that at the end of this class, we need to know the relative strength of acid and bases. Relative strength of acids and bases. Okay? And the third one is that at the end of this class, we should be able to know how to neutralize an acid. Neutralizing an acid should be one of the things we must learn in this class. And the last one, which is formation of salt, how salt is being formed. We have different way of salts being formed. So we're going to look at various ones that we need to know, and the method of preparing soluble and insoluble salts, testing for different salts. These tests will be under the part 2 because we are stopping under insoluble salts for this class. Okay, part 2. Part 2, in our next class, we'll be able to know how to calculate water of crystallization, okay? And the second one, to know how solubility of salt in water, we need to know what are the things they use in measuring the solubility of salts in water. That means we have to calculate the solubility, and we have to know more about the solubility curves, okay? And we'll talk more on titration, because I know you by now you've started practicals. And first and foremost, I know volumetric analysis and all this is the first thing you must do after knowing all the apparatus. So we'll talk about it theoretically too, as well as to be in line with the practical you're having right now. So I know, and I'm so sure it will be a wonderful class for all of us. Okay, the first thing on the list is acids and alkalis. Acids and alkalis. Okay, if you look at it, some substances such as tomato ketchup, our tomato ketchup that we use for garnishing and to do some things in the kitchen. So we have the avocado pear. Avocado pear is a green pear that is somehow oblong in shape. Then we have the orange juice. So in all these substances, or all these kind of things that I just listed and more, etc. is there. You can have the list is unending. So you can have acid, one sort of acid or the other inside all these things, okay? Just like you have your citric acid, you have ascorbic, you have vinegar, there are lots of them. So here is kind of part of physical properties of acid. The word acid means sour. They have this sour taste. I didn't ask you to taste it, but that's how it is. They have sour taste. That's number one. And all acids possess these properties. If you try to put tomato ketchup on your tongue, you feel that sour kind of taste. Same thing with avocado. It be as if they put some little what's the kind of thing that can give you sour taste? You know what I mean? So they are also soluble in water. Acids are soluble in water, and they are corrosive. They are corrosive in the sense that they can cause damage. They can deteriorate your body system. They can affect you one way or the other. So an acid is a substance which in aqueous solution produces hydronium ion. You can call hydronium ion same thing as ozonium ion. That's H3O with your positive superscript on it as the only positive ion. They produce that as the only what? Positive ion. Whenever you have this, you know we are talking of acid. Okay, there are two classes of acid. Organic acid occur as natural products in plants and animals. E.g., you have your ethanoic, just like you have it in vinegar, your lactic acid, which is seen in milk, your citric, which is seen in lemon, your ascorbic, which is seen in orange, and all that. So you have them different types. So the second one is inorganic acids, can be prepared from mineral elements or inorganic matter. E.g., you have hydrochloric acid, you have hydrogen tetraoxosulfate acid, you have hydrogen trioxo nitrate 5, that's HNO3 acid. Okay, so alkalines. What do you understand by alkalines? Alkalines are very different and are chemical opposites of acid. Okay, they are chemical. When you say something, so you have to see their properties there. So e.g., you have your milk of magnesia liquid. You know, when you have stomach upset, you can't sleep, you can't sit, you can't do anything, you are so much in pain. They'll give you this as a result of indigestion or something. You take milk of magnesia liquid and immediately you feel this awesome relief. Okay, what happens there is that the milk will attract the hydrogen ion and giving you water. So you sweat it out. In short, you sweat it out, and if probably you go to toilet. So these are examples of alkalis. Then they will remove sharp taste from an acid. That's one of the properties. Okay, they have a soapy feel. When you feel them, they give you this feel of soap. Okay, chemists use substances called indicators which change color when they are added to acids and alkalines. Just like the one we use in our laboratories, you have to put it in the acid. So by the time you are titrating, you realize that just a sharp color change. That's why you must be meticulous while carrying that out. So whenever you notice that sharp change, you now drop it in drops. You don't rush. Okay, so you can have a neutral solution. So this is it, indicators and their color in acid and alkaline solution. You have indicators here, you have color in acid and color in alkaline solution. You have blue litmus, we turn to red in acid and blue in alkaline. Methyl orange, we turn pink in acid and yellow in alkaline. Methyl red, we turn red in acid and yellow in alkaline. Phenolphthalein, we turn colorless in acid. You won't even know you put anything in there. And in alkaline solution, it will turn pink. Okay, when you put your base in the acid, you have your end color to be pink. So red litmus paper, it will be red in acid and blue in what? Alkaline solution. So to obtain an idea of how acidic and alkaline a substance is, we use an indicator. We use another indicator known as what? Universal indicator. Okay, it is mixture of many other indicators. The color shown by the indicator can be matched against a pH scale. For instance, in the laboratory, when something practical is being done or experiment is being carried on, you realize that when you put an indicator it changes the color of acid, and when you run the it changes the color of the what's it called, the base, and when you run acid into it from your burette, you realize a little color change at some point. So you have to be dropping it in drops until when you see, you'll be shaking it as well, so you won't add too much of acid to it. At that point, there will be color change. That means there's neutralization. There's this end color. So with that end color, if you use the pH scale, it will help you to know maybe it's now neutral, or it's still acidic, or it's still alkaline. Maybe you have too much of. That's why you must be very, very careful when carrying out your practical. So the pH scale was developed by this guy. He's from Scandinavia. Okay, he's a Scandinavian chemist from all this Norway, Denmark area. So his name is called Sorensen. So he was the one that developed the pH scale. As you can see here, this number 1, as in pH 1, that's very acidic. So acidic nature increases from what? From 6 to 1. So 1 is the highest acidic, the most acidic acid here, or the most concentrated acid. And when you look at 7, it's neutral, it's just green. So look at the colors for the alkaline, when you have slight alkaline, and the maximum one, the most alkaline solution, is being seen in 14. So this pH scale universal indicator, okay, so you can just take your time and look through. And theories of acid and bases. You know, there are lots of chemists that worked before we can, you know, as a scientist, there should be so many hypotheses, suggestions, and all that. But if they now carry out and they see that the theory, the hypothesis, or the suggestion is meaningful, they can now accept it as universal theory. So there are some guys that worked on acid base and wherever here. The first guy on my list is called Anthony Lavoisier. He's a French chemist. Okay, he was the one that suggested that acid were substances that contain oxygen, but it was proven wrong. It's a suggestion anyway, because after this compound hydrohalic, when you have halogen mixed with hydrogen, just like hydrogen chloride, hydrogen bromide, fluoride, and all that, they realize that it's not all acid that contain oxygen, because you can't see oxygen here and they are all acids. Okay, so there's another guy that modified the suggestion of this guy. His name is Humphrey Davy. Okay, Davy in 1810 suggested that all acid contain hydrogen as important elements. However, it was pointed out there were many hydrogen containing compounds that were not acids. So they tried, but it wasn't working out for them. So the third guy was a German chemist, Justus von Liebig. Okay, Liebig suggested that acid were substances that can react with metal to produce hydrogen gas. Okay, there's another guy, Swedish chemist Svante Arrhenius. Okay, he was the one that suggested that since acid solution were electrolytes, electrolyte means they have charges, they can conduct electricity. Okay, their solution contain many ions such as hydrogen ion and hydroxide ion when they dissolve in water. And there were two guys, they did their work independently. Their names are Jonas Brosted and Thomas Lowry. So Lowry and Brosted did their experiments, and they find out a more general definition of acid and base, which took a great step forward. So the theory is now a Brosted-Lowry theory. It's like a combination of the two names of acid and base. So let's look at the theory. What does it say? The first one here says an acid, they define an acid as hydrogen ion or proton donor. Okay, they give out the hydrogen ion or their proton. Okay, a base as an hydrogen what acceptor is the one that does accept the hydrogen ion. So here you have the acid, you have the base, and this is the final product. If a substance can behave both as bromelluric acid and base, then it is amphoteric. Okay, if you have a substance that conform to this theory as an acid or as a base, then it is called what? Amphoteric. Water has this ability. Water can behave as an acid and likewise as a base. It can also react with bases such as ammonia and all that, except the acid. So you see, ammonia is a base and water is acting as acid there. So it's donating what? Hydrogen ion to what? Ammonia to become what? Ammonium ion. Okay, same thing here. So this is the right when ammonia is behaving like base in the presence of real acid, which is hydrochloric acid. This is what you have, like ammonium chloride. Okay, relative strength of acids and base. When you talk of relative, you are comparing strength between two or more things. Okay, the strength of an acid is found by comparing one acid with another, and it is dependent on how many molecules dissociate or ionize when it's dissolved in water. When you dissolve an acid in water, you know, the ion will separate out. You have H plus and OH minus. Okay, the ability of that acid to ionize when dissolved in water is what you call strength of acid. Likewise, base also. So that of base depends on dissociation of base in aqueous solution. When you talk of aqueous solution, when you add water to it could be a solute or solvent, you have water, you add water to it, you have an aqueous solution. So strong and weak acid. A typical strong acid is hydrochloric acid. It is formed by dissolving what? Hydrochloric acid in water. Here the ions form separate completely. Ion form separates completely. Okay, so we have hydrogen chloride there. You put water, and what do you have? You have the ion separate out. You have the hydrogen ion and chlorine ion. So this is the normal, these are normal equation. The first one is the word equation. Okay. So if we move ahead, we have for hydrochloric acid, all hydrogen chloride molecule breaks up to form what? Hydrogen ion and chlorine ion. Any acid that behaves this way is termed a strong acid. So it's all the molecule, note it, all the hydrogen chloride molecule breaks up to form what? Hydrogen ion and chlorine ion. That's why it's called what? A strong acid. Both sulfuric acid and nitric acid, we're supposed to be using a opaque name. So sulfuric is same thing as tetraoxosulfate 6 acid, and nitric acid is same thing as what? Triosonitrate 5 acid. Also behave this way and are therefore termed what? Strong acid. So all of them have high concentration of hydrogen ion in solution and have low pH. Their solution are good conductor of electricity because they are good electrolytes. Okay, they react quickly with metal, base, and metal carbonates. When strong acid are neutralized by strong alkaline, the following reaction takes place. So this is what you have ionically. Okay, ionically, that means H plus is from acid and OH is from alkaline or base, as the case may be. So a weak acid such as ethanoic acid, which is from vinegar. So vinegar is an example of a weak acid, which is CH3COOH. That's an example. ethanoic acid. Okay, produces a few hydrogen ion when it dissolves in water, compared to strong, all the hydrogen ion is not separated out when it's being dissolved. So it only produces few hydrogen ion when it dissolves in water compared to strong acid. That's why it's a weak acid. Okay, that's why you can call it a weak acid. So for example, ethanoic acid dissolved in water will give you hydrogen ion and ethanoate. So this is the equation. Other example, you have citric, you have carbonic acid, you have sulfurous, you have ascorbic, and the likes. So solution of weak acid are poorer conductor of electricity compared to strong acid. They have they are slower in reaction with metal, base, and carbonate. Note the fact that acid ionizing aqueous solution to produce hydrogen ion does not mean it is concentrated. So there are two things involved. When you are talking of the ion being ionized in aqueous solution, you are talking of the strength, okay, the relative strength of the acids. That's what you are talking of. So when you are talking of concentration, you are now talking about maybe the proportion of acid with water being added. Okay, the acid present in aqueous solution and the proportion of water being added. That's when you can talk of concentration. So a strong acid is still a strong acid even when it is in dilute solution. A weak acid is always a weak acid even if it is in concentrated solution. Even if you don't have water to a weak acid, it's still a weak acid. Okay, and if you add water to a concentrated strong acid, it's still a strong acid. So strong and weak bases. An alkaline is a base. I want to pay close attention to all this definition. An alkaline is a base which produces hydroxide ion, OH minus, when dissolved in water. That's why you have it AQ. That's aqueous, addition of water. Okay, when dissolved in water. That means alkaline is a is a soluble base. That's what it means. When dissolved in water, okay, is a base when it produces OH ion when dissolved in water. So alkaline and base are the same, provided that is a soluble base. If it's insoluble, then you take base separately. Sodium hydroxide is a strong alkaline because when dissolved in water, its lattice breaks up completely to produce ion. This is an example. So some common strong alkaline you have here too. Okay, base. Let's define base. A base is a substance which will neutralize an acid to yield salt and water only. Oxide and hydroxide of metal are bases, okay, just like you have them here. So strong alkaline produces large quantity of hydroxide ion and strong pH. Note that strong alkalines produces large quantity of hydroxide ion and they are strong in pH too. Okay, when you are talking of strong, you are talking of from something like 10 to 14. Okay, other common strong soluble bases include potassium hydroxide. A weak alkaline such as ammonia produces fewer hydroxide ion, hydroxide ion when dissolved in water than strong soluble base of the same concentration. Then another thing you should note about weak alkaline is partially ionized. It's not completely ionized. A lower pH than a strong, still above 7, could be between 8, 9 or so. So that's it. Ammonia is an example. So neutralizing an acid. What happens when you are neutralizing an acid? In the laboratory, to neutralize a common acid like HCl acid, that's hydrochloric acid, you can use an alkaline such as what? Sodium hydroxide. If the pH is measured, as some sodium hydroxide solution is added to it, the pH increases. Why do you think the pH increases? You know, for acid, the pH is from 6 to 1, and a strong acid for that matter like HCl should fall between 1 and 3. Okay, as you now add sodium hydroxide to it, the pH will increase. That means it's tending towards neutral and alkaline solution. Okay, but if equal volume of same concentration of HCl acid and sodium hydroxide are added to one another, the resulting solution is found to have a pH of 7. That will only tell you that when you are carrying out your practical, you have to be meticulous. You have to be very careful, so you don't have too much of acid or too much of base. What you want to achieve at that point is a neutralized solution. Okay, you want to neutralize the acid as well as base to have a neutral solution. So the acid has been neutralized and a neutral solution has been formed when you have it this way in correct proportion. So as we've seen, we are not interested in normal equation, we are interested in ionic, okay, equation. That's why I give you this. So same thing, you have to, when you're talking of acid and base, you have to show how they accept proton or hydrogen ion and how they donate. That's what we are interested in. Formation of salts. A salt is compound derived from acid by replacing all or part of ionizable hydrogen contained in an acid by metal or ammonium ion. Most salts are neutralization products of acids and base. That is, acid plus base will give you what? Salt and water. Ionically, you have it like this. Okay, this from acid, from base, and you have the salt and water. Okay, you have to balance your equation in anything you are doing. So this is an example. You have HNO3 and sodium hydroxide will give you what? Sodium triosonitrate 5 salts with water, 2 moles of water. So types of salts, we have different types of salt. The first one on my list is normal salt. It's a compound that has been formed when all the hydrogen ion, replaceable hydrogen ion of an acid have been completely replaced by metal ion or ammonium ion. When all the hydrogen ion, that's H plus, has been completely, nothing is remaining. You know, some they have partial ionization, but this, for a normal salt, that means you have it all replaced by what? Either metal or ammonium ion. So these are normal salt can be classified as those which are soluble in water and those which are insoluble in water. The following salts are soluble in cold water. All nitrates are soluble. Those are the inferences that you carry out before you say something is present during your practical when you are testing for all these ion. Okay, all nitrates are soluble in water. Take that any day, anytime. All common sodium, potassium, and ammonium salts are what? Soluble in cold water. All chloride except what? Lead, Pb, silver, and what? Mercury. Those 3 are not soluble in cold water. All sulfates except what? Lead, barium, and calcium are insoluble in cold water. So you have to know that if the acid being neutralized is hydrochloric acid, the salt called chloride are formed. Other types of salts can form with other acids. So these are summary of the kind of salt that will be formed. If you use this acid, you use this salt, this is what you get. So take your time and have a look at them. Okay, methods of preparing soluble salts. We have 4 general methods of preparing soluble salts. You can prepare it by using acid, reacting acid with metal. Okay, this can be used with less reactive metal. When you do just metal, the normal metal with acid, it's not their carbonate, it's not their oxide or anything. You just take the metal with acid. All the metal in here are less reactive. So it will be dangerous to use reactive metal as sodium. Sodium is very, very reactive, okay, in this type of reaction. So how can you know all the metals you can use in this situation, since we know that less reactive metals only can be used? So the metal usually used there is what? I gave it an acronym called MASITs. Okay, MASIT means magnesium, aluminium, zinc, iron, and tin rather. All those 5 metals can react with acid directly. So you can just take a look. This is the formula. When you have the hydrogen ion from acid reacting with electron, hydrogen gas will always be formed. So this is what, when you have magnesium ribbon being added to what? Nitric acid. Nitric acid is H2NO3. That's hydrogen triazonitrate 5. Okay, how will you test the gas to show that it was hydrogen? The first thing you must do is to write your equation and you balance it. So when you write your equation, you have it that is hydrogen gas that will be evolved. Okay, what would the name and formula of the compound produced during the tests? What's the name that you suggest? After writing your equation, you can always name it, okay? For instance, this one is what? Magnesium triazo what? Nitrate what? Since you have 6 oxygen here, you have for nitrogen you have 7, that's 2, 5. It remains 2 to have your alternate state. So 6 times minus 2 will give you minus 12. 5 times 2 will give you 10. So that means you have 2 of these. That's magnesium 2 what? Triazonitrate what? 5. That's the compound you get. Why hydrogen gas will be evolved. Excess magnesium can be filtered off by filtration, and the magnesium triazonitrate 5 solution is evaporated slowly to form saturated solution. When you want to evaporate the after what's it called, after filtering it, you have to evaporate, so it will be saturated solution. Saturated solution means the concentrated salt, so you cannot leave it to evaporate. Okay, you can remove it from the Bunsen burner and put it down, but before you can remove it, you have to test it with glass rod. When you dip a glass rod into it, you know maybe it's already crystallized. You know, when you remove the glass rod, the body of the glass rod will show you either is a crystallized solution now, or you have to heat more. So that's it. The second one is acid and carbonate. When you react these two together, this is what you have. Okay, an effervescence will happen. Effervescence means carbon 4 oxide will be evolved. That means it will be liberated. Okay, so anything you have to write your equation out first. You have to write your equation out first. So the third one is all about acid and alkaline. Soluble base. You know, don't forget what we say. Alkaline are soluble base that produces what? They produce OH minus. That's hydroxide ion. Any day, anytime. That's the definition of alkaline. So this method is generally used for preparing the salt that are very reactive metal, very reactive metals such as sodium, potassium, and it will certainly be too dangerous to add metal directly to the acid. Okay, that's one of the precautions you have to take in the lab. You don't add acid to base like or alkalines like sodium hydroxide or potassium hydroxide. The whole lab will explode. Okay, it's a splash everywhere. We solve the problem indirectly and use an alkaline which contains particular reactive metal whose salt we wish to prepare. So we don't react them directly, just like the first situation. They don't go directly with metal, they go with what? Hydroxide of the metal. So this is what you have there. Soluble bases, which are alkalines, insoluble bases, which you call base. Okay, because in this neutralization reaction, both reactants are in solution. A special technique called titration is used. Your acid, you have to dissolve it in water, or you have to add water to it to make it an aqueous, okay, the one that will have charge, that's H plus and Cl minus for the acid. And that's when you can now react it with what? Sodium hydroxide. They are both in what? Solution. So a special technique called titration is required. That's why you titrate in the lab against this and this. They are both soluble reactants in solution. So you have to take this method to calculate their volume or the end point. And another thing you must note is that an indicator is used to show when the alkaline has been neutralized completely by acid. This is called end point. That's when you must be careful. When you are running your acid from the burette into your beaker where your base is, you have to be shaking often. Just a little tilt, so you know when the thing is changing. Okay, this is the equation for the reaction. Then the last one, which is acid plus insoluble base. Insoluble base are salts of unreactive metals such as lead and copper. In these two cases, you can react them with what? Acid to get, in situation of copper oxide, copper 2 oxide reacting with sodium hydrogen tetrahydrosulfate 6, you have copper 2 tetrahydrosulfate 6 and what? Water. So this is the ionic equation. Don't forget, after writing the main equation, you have to do the ionic equation. Method of preparing insoluble salts. An insoluble salts such as barium sulfate can be prepared by precipitation. In this case, solution of two chosen soluble salts are mixed. Okay, when you chose two salts, soluble salts, you mix them together to produce barium sulfate, barium chloride, and sodium sulfate can be used. Okay, to produce barium sulfate, you can use this and this. Those are the two salts you react together. They are both soluble, right? Barium chloride is soluble, sodium sulfate is soluble, because in this case, to produce this insoluble salt, which is barium sulfate, you have to react two choosing soluble salts. You have to mix them together. So this is what you have: barium chloride with disodium what? Tetrahydrosulfate 4 or 6, sorry, tetrahydrosulfate 6, which will give you barium sulfate and sodium chloride, and this is insoluble. Okay, that's how to prepare your insoluble salts. This is the ionic equation, and this method is sometimes known as what? Double decomposition. Salts like barium sulfate dissolve to a little extent, to a small extent, dissolve, it precipitates. You feel it's dissolving, but it's just like maybe 0.02 of it dissolve, and that's why you can call them sparingly soluble salts. Okay, stay happy and enjoy your week.